Hello, and welcome to Linear Algebra. This is lecture 34, Spectral Theorems. So, last time, we talked about adjoint maps. Right, so if you have a linear map going from V to W, then the adjoint map goes from W to V, and it is characterized by the property that the inner product of T acting on V paired with W is equal to the inner product of V paired with the adjoint of T acting on W. Right? So notice that this inner product is happening on W, and this inner product is happening on V. So this time, what we want to see are consequences for diagonalizability. Okay, so let me remind you about more things we saw last time, but now having to do with eigenvalues. So last time we saw that all of the eigenvalues of a self-adjoint map, right? So this would be the T, the linear map from a vector space to itself, that is equal to its adjoint, or equivalently, this says in terms of inner products that you can move the T from one side to the other. Right, so we saw that all eigenvalues of a self-adjoint map are real numbers. So even if you're working over the complex numbers, if you have a self-adjoint map, then the eigenvalues are automatically real. Also, we saw that eigenvectors of T corresponding to distinct eigenvalues are orthogonal to each other, right? So previously we had seen that in general, the eigenvectors corresponding to distinct eigenvalues of a linear map are linearly independent, right? Now, if you have a self-adjoint map, we can strengthen that to saying that eigenvectors coming from distinct eigenvalues are orthogonal to each other. Okay, great. So let's jump straight into the main theorem. This is known as the spectral theorem. For self-adjoint maps and Hermitian matrices. Right, so remember, Hermitian matrices are just matrices that are equal to their conjugate adjoint. If they have real entries, that means that they are equal to their transpose, and in that case, we call them symmetric. Okay, I think I've said this before, but let me say it again. Spectral here is because we usually use spectrum to refer to the eigenvalues of a map. It comes from way back when Newton started talking about the spectrum of light, and the spooky aspect of talking about spectra is on purpose. It was like there were all these different colors contained in white light that you couldn't see until you used a prism to separate them out. So that's why we use spectral. So here's spectral theorem. You can also think about it as a theorem about the eigenvalues of self-adjoint maps and Hermitian matrices. But really, it's a theorem about diagonalizability. So here we go. If V is a finite dimensional inner product space, and T, linear map from V to itself, is self-adjoint, then there is an orthonormal basis of V consisting of eigenvectors of T, right? So remember, being diagonalizable is the same as saying that there is an eigenbasis. There is a basis of the vector space consisting entirely of eigenvectors. So here we have a wonderful theorem, right? This says that it's enough to know that an operator is self-adjoint to know that there is an orthonormal basis of eigenvectors. So not only is it diagonalizable, it is orthogonally diagonalizable. You can do it with an orthonormal basis. And again, this is fantastic because knowing that there is an orthonormal basis of eigenvectors takes work. Knowing that a map is self-adjoint is really quick most of the time. Certainly for matrices, it's really quick to know whether or not a matrix is Hermitian. Let's state the theorem for Hermitian matrices. It's the same theorem just for matrices. So say you have a matrix with complex coefficients, so including the case where you just have real coefficients. So we're saying that it is Hermitian, right? Or the real case, let's say you have real coefficients. It is symmetric. Then there is a unitary, respectively orthogonal, matrix U, same size, n by n, coefficients of whatever field we're working in, such that A is equal to U times the diagonal matrix with diagonal entries lambda1 through lambda n being the eigenvalues of A times U star, 1 through lambda n, are the necessarily real eigenvalues of A. Okay, so that is the spectral theorem. It's one of the most important theorems in this class. The proof is going to be by induction over the dimension. Okay, so we'll induct over the dimension n of V. Okay, so if V is one-dimensional, there's nothing to prove, right? Because if you have a linear map from V to itself, then every matrix associated to it is just a one-by-one matrix, and so it's automatically diagonal. So there's nothing to prove. So suppose we know the theorem for all vector spaces of dimension less than n. Okay? Now, T is a self-adjoint map. So since T is self-adjoint, we know that it has an eigenvector. Say V, satisfying that T of V is equal to lambda V with V not equal to 0. Okay, actually, so this we know for an arbitrary linear map when we're working over the complex numbers, we know that there are eigenvectors. So what's special here is we know that lambda is a real number, and we know that any eigenvectors corresponding to other eigenvalues have to be orthogonal to V. Okay, so let's let U be span of the orthogonal complement. Then the claim, and here's where we're using self-adjointness, claim is that if U is any vector in capital U, then T of U is again a vector in capital U. Okay, so we say that T preserves capital U. It sends vectors in capital U to vectors in capital U. Okay, and indeed, so what do we need to check? You give me a vector in capital U, so that means that it is orthogonal to V. And I need to check that T of it is in capital U. That means T of it is also orthogonal to V. So I take this inner product, I need to show that it's equal to 0, right? But I know that T is self-adjoint, so I can write this inner product with T on the other side without changing anything, right? And I know that V is a eigenvector, so T of V is equal to lambda V. And I know that U and V are orthogonal to each other, so that's equal to 0. And just for emphasis, I'll say this shows that T of U is an element of capital U. Now, since the dimension of capital U is strictly less than n, our inductive hypothesis applied to T restricted to U allows us to find an orthonormal basis, let's call it U1 through UN minus 1, of capital U consisting of eigenvectors of T. Then let's just add V to this list. This is an orthonormal so sorry, let me change that. Let's take V divided by the length of V, because I never said that V was a unit vector. So let's make it a unit vector. Now we have an orthonormal basis of V consisting of eigenvectors of capital T, right? So here we're using that it's self-adjoint to say that this eigenvector is orthogonal to all of the other eigenvectors here. Right, actually, sorry, that it's much simpler than that. We know that this one is orthogonal to all these other ones because U is the orthogonal complement to V. So all of the vectors in U are orthogonal to V. Right. So we only used self-adjointness to establish this claim. And then as part of our inductive hypothesis, we used that T restricted to U is also a self-adjoint map. Okay, great. So that proves the spectral theorem. Now, the factorization, when you write A as U times this diagonal matrix times U star, this is known as the spectral decomposition of capital A. Okay, so let's talk about a few consequences, a few simple ways of using this. There are many consequences of the spectral theorem. This is a standard tool that you would use from now on, and in infinite dimensions, the corresponding theorem is used all the time. But for now, let's just talk about a few simple consequences. So one consequence, is that we're guaranteed that the algorithm for the singular value decomposition of an arbitrary matrix will work. Right? Remember, there's a step in the algorithm for finding the singular value decomposition where you need to find an orthonormal basis of AA star or A star A. And because those matrices are self-adjoint, we're now guaranteed that there is an orthonormal eigenbasis. Okay, another consequence is that we can easily recognize when a Hermitian matrix or a self-adjoint map has only positive eigenvalues. Right, so, and this criterion goes as follows. Suppose you have a Hermitian matrix, then it has only positive eigenvalues if and only if the inner product of A applied to X against X is positive for every X in Cn that's not equal to 0. Okay, why would you want to know if a map has only positive eigenvalues? Well, this is something that you use in calculus, right? Multivariable calculus. In one variable calculus, we know that critical points of a function happen when the function's derivative is equal to 0, and then we look at the second derivative to decide whether it is a maximum or a minimum, right? If it is if the second derivative is positive, then we know that the function looks roughly like a parabola that's opening up, and so it would be a minimum. And if the second derivative is negative, then we know that the function looks roughly like a parabola opening down, and so this point would be a maximum. Well, in higher dimensions, you have to look at all of the different ways of approaching your critical point. So when you look at the second derivative, it is actually a matrix, and you want to know if this matrix will tell you, does it look like a paraboloid opening down or a paraboloid opening up? And that means, are the eigenvalues all positive or all negative, right? Notice that you could have eigenvalues of mixed signs that corresponds to saddle points. So, okay, so we want to know if all of the eigenvalues are positive. And so it's nice to have a criterion like this one that will tell us if we have positive eigenvalues. Okay, great. So that's why we would want to prove this. Now let's go ahead and prove it. Okay, it's an if and only if, so we should prove both directions. So let's start with this direction. This is the easier direction. Well, they're both pretty easy, but this is the easier one. So in this case, let's say we know that the inner product of AX against X is strictly positive for all non-zero X in Cn. Then in particular, this is true when X is an eigenvector. Let's say AX is equal to lambda X. Thus, we have that, let's write it like this, lambda XX is equal to lambda X inner product with X, which is equal to A X inner product with X, and then this is positive, strictly positive. And now since we know that this is strictly positive, well, as long as X is not 0, which is not because it's an eigenvector, so we know this is strictly positive, then this product will be positive precisely when lambda is positive. Right? So that takes care of that direction. Let's prove the other direction. So assume that all of eigenvalues of A are positive. We want to show that the inner product of A X with X is positive for all non-zero vectors in Cn. Okay, great. So the reason why this is easy now is because we have the spectral theorem. So using the spectral theorem, we can find n by n matrix U is unitary such that A is equal to U times the diagonal matrix with entries to the eigenvalues of A times U star. Then for any X not equal to 0, let's let Y be equal to U star X, right? And let's say that this has entries U1 through UN. And note that, okay, the inner product of A x against x, I'm going to write that as U, inner product of U times the diagonal matrix, lambda 1 through lambda n, times U star times x paired with x. Now I'm going to move this U to the other side, right? I have to pay with an adjoint, right, with a conjugate transpose. So I end up with diagonal lambda 1 lambda n times U star acting on x paired with U star of x. So in terms of y, I can write this as diagonal matrix with entries lambda 1 lambda n applied to y paired with y. And now because this is the standard inner product on Cn, I can write this as the sum, j goes from 1 to n, of the jth entry of the first vector, so this would be lambda j yj, times the complex conjugate of the jth entry of the second vector. Right? And then this we just recognize as the sum, j goes from 1 to n of lambda j times the modulus of yj squared. And now we notice that that is strictly positive because our assumption is that all of the eigenvalues of A are positive, and the moduli of yj, well, I don't know if they're all strictly positive, but because y is not 0, at least one of them is strictly positive, and so then this sum is strictly positive. Right? So that proves the second direction, and that establishes the theorem. Okay, another consequence, and this is one of my favorite consequences. Is that when A is Hermitian, it is easy to compute functions of A, right? So what do I mean? Well, let's start with something very easy. So if A is equal to U d U star with D the diagonal matrix, right? So like that, then, well, let's say you wanted to compute just A cubed, right? So A cubed would be just U d U star cubed, or U d U star, U d U star, U d U star, right? But now every time there's a U star U, that's equal to the identity. So I can write this as U and then D cubed U star. So, right, that is to say, A cubed is just U and then the diagonal matrix lambda 1 cubed to lambda n cubed, and then U star. Okay. Similarly, if you want to compute the kth power of the matrix A, all you have to do is multiply U times the diagonal matrix where you take the kth power of each eigenvalue, and then U star. Okay, so as soon as you know U, D, and U star, then you can compute any power of A by computing that power of D, which is trivial, and then just multiplying on the left and right by U and U star. Okay, but then why stop at just the positive powers or the integer powers? So if all of the eigenvalues of A are positive, then A has a positive square root, right? So you can take the square root of a matrix, right? So the square root of the matrix would be just u, and then take the diagonal matrix whose entries are square root of lambda 1 through square root of lambda n, and then just multiply by u star. Okay. Okay, but why stop there? Right? So if a function can be expressed as a power series, then we can apply it to a Hermitian matrix. I'm not saying it'll automatically converge, but you can apply it, and if it converges, then you've figured out how to apply that function to your matrix. So here's an example where convergence isn't a problem. So recall that the exponential map has a power series. You can write it as 1 plus x squared divided by 2 plus x cubed divided by 3 factorial, and so on, right? So briefly, the sum k goes from 0 to infinity of x to the k divided by k factorial. So define e to the a for any Hermitian matrix A to be, so I'm just going to take this, just like we've done, we've plugged in a matrix to a polynomial, now we're going to plug in this matrix to the power series, right? So I'm going to get the identity plus a squared divided by 2 plus a cubed divided by 3 factorial, and so on. Or briefly, I'll just say the sum k goes from 0 to infinity of a to the k divided by k factorial. Okay, now this definition makes sense regardless of whether or not A is Hermitian or not. But if A is Hermitian, and I have A is equal to U times diagonal matrix lambda 1 through lambda n U star, then e to the A, so this sum, k goes from 0 to infinity of a to the k factorial, well, we just saw that it's easy to compute a to the k because all you do is you put u, and then you put the diagonal matrix where you replace every eigenvalue with its kth power, and then you put u star. Okay, now notice that here of this sum, I could take as a common factor u and as another common factor u star. So I could write this as u times the sum k goes from 1 to infinity of this diagonal matrix, lambda 1 to the k to lambda n to the k divided by k factorial, and then u star. Okay, let's keep going. If you do a sum of diagonal matrices, then of course you're just doing a sum of each diagonal entry, right? So I can write this as u times the diagonal entry, diagonal matrix, where in each entry I'm doing the sum k goes from 0 to infinity, k lambda 1 to the k over k factorial, sum k goes from 0 to infinity of lambda n to the k divided by k factorial u star. And of course, you see where I'm going with this. This is equal to u times the diagonal matrix where I put e to the lambda 1 in the first entry and so on, keep the lambda n in the last entry, and then u star. So see, you can compute the exponential of a matrix, right? So if your matrix is given as u diagonal u star, then all you do is you keep the u in the u star, and in diagonal matrix, you replace each eigenvalue with its exponential. Okay, so that's wonderful. You can compute functions of your matrix. And this is really useful when you're looking at, say, differential equations. I'll have more to say about that in a different lecture. It is worth remarking, one should not get too carried away. Not everything carries over to matrices. So, for example, e to the a plus b equal to e to the a times a to the b is only true if a and b commute. Right. So, although you can define the exponential of a matrix, so I can define each of these terms, right? The exponential identity that works great for numbers doesn't work for matrices in general. It's only if they commute that you have this. Okay. Okay, wonderful. Now, there is a simple extension of the spectral theorem that we just proved for Hermitian matrices to a slightly larger class of matrices. Well, to a larger class of matrices. So let's think about this. Right, so the thing to note is that the spectral decomposition is an if and only if. So if D is a diagonal matrix with real entries, U is a unitary matrix, and U is a unitary matrix, then the matrix A, which is given by U, D, U star, is Hermitian. Right. So wonderful. If you have a spectral decomposition, then you're Hermitian, and we just proved in the spectral theorem that if you're Hermitian, then you have a spectral decomposition. Great. So what if we like the spectral decomposition, but we don't want to require that D have real entries? Right? So what if we allow D to be a diagonal matrix with complex entries, right? So what would that tell us about those A's that can be written like this? Well, notice that if A is U diagonal lambda 1 through lambda n, U star with lambda I in the complex numbers, then let's say star, well, A star would be equal to U, and then the diagonal matrix with the complex conjugate of the eigenvalues we had before in the center. So here the thing to notice is that if you do A star, right, you would get, well, let's write it out. So I would get U, D, U star, and then I take the star of this, so I would get U, D star, U star. And here I have U star U, so that becomes the identity, and I end up with U, D star, U star. And let's go ahead and write that out. D times D star, well, this is D and this is D star. They're both diagonal, so I'm just going to multiply the corresponding diagonal entries. And so I would get diagonal of lambda 1 modulus squared through to lambda n. modulus squared, and then U star. Right, but of course, d star is going to be the same as d star d. It doesn't matter what order you multiply those in, because you're just multiplying in each entry, and in each entry, you're just doing multiplication in the complex numbers. So if I had done a star, sorry, a star a, instead, this would have looked like u d star u star times u d u. Again, the u star u in the center there becomes the identity, so I don't have to write it down. And I end up with u d star d u star, and then that's u diagonal lambda 1 modulus squared through to lambda n modulus squared, and then u star. So if we're in this setting where we have u d u star, and d is diagonal but possibly complex, then a star is equal to a star a. So thus a star is equal to a star a whenever a can be unitarily diagonalized. Okay, so we give that a name. An n by n matrix is said to be normal. It's very unfortunate. It's not a very descriptive name, but what can you do? It's a normal matrix if it commutes with its conjugate transpose. Okay, so I want to prove the spectral theorem for normal matrices, right? I want to prove that this is an if and only if. This thing we noticed is an if and only if. To do that, first let's prove really a lemma for us, but it's such an interesting lemma that it's called a theorem, and it even gets a name. This is the Surety Composition. So here's what the Surety Composition says. Suppose V is a finite dimensional complex inner product space. And let's take T to be any linear map from V to V. There is an orthonormal basis B of V such that the matrix associated to T with respect to B is upper triangular. Okay, so you could say we already know this. We know that every matrix, every linear map over using the complex numbers is associated to an upper triangular matrix. That's true. What's new here is that it's an orthonormal basis, right? So you can triangularize your map using an orthonormal basis, right? So of course, there's also a statement for matrices. Equivalently, if A is a n by n matrix with complex entries, there is a unitary matrix U, also of size n by n, and an upper triangular matrix, call it C, n by n, such that A is equal to U, C, U star. Okay, so every matrix with complex entries is similar to a upper triangular matrix. That we already knew, but now we know that it's similar with a unitary change of basis matrix. Okay, the proof is very quick. So we know that we can find S n by n with complex entries invertible, and an upper triangular matrix B with complex coefficients such that A is equal to S, B, S inverse. So this is the triangularizability result that we've already shown. So one thing we've shown since then is the QR decomposition. So let's let S be equal to Q times R. Let this be a QR decomposition of S. Right, so Q is unitary. And R is upper triangular. Right, remember the R stands for right, so it's like right triangular, which is the same as upper triangular. Then A is equal to, well, S, but I can write S as Q times R. And then B, and then S inverse, so that's Q times R inverse. Now I can write that as Q, and then R, B, R inverse, and then Q inverse. But because Q is unitary, Q inverse is equal to Q star. And now just note that this is upper triangular. So this I can write as Q, C, Q star with C upper triangular. Okay, so that proves the Surety composition. And as I mentioned, that will be used for the spectral theorem for normal matrices. Of course, you can also express this for linear maps, but let me save time by only doing the matrix statement. So A is unitarily diagonalizable, which is to say there is an orthonormal basis of Cn consisting of eigenvectors of A if and only if A is normal. A commutes with A star. Okay. Again, this is an awesome theorem because being unitarily diagonalizable is in principle something that requires a lot of computation to check, right? You have to construct an orthonormal eigenbasis of eigenvectors. On the other hand, checking that A commutes with its adjoint is something very quick and easy to check. Okay, so we've done half of this already. We've checked that if it's unitarily diagonalizable, then it is a normal matrix. That was our motivation for the definition of normal matrix. So all that's left is to check the other way around, right? That so we should assume that A is normal, right? That is, A commutes with its adjoint, right? Want to show A is unitarily diagonalizable. Okay, great. So the Surety composition of A, say A is equal to U, C, U star, implies, so the surety, let's say using the surety composition of A, we find that A star A is U C star U star U C U star. So again, the U stars in the center cancel, so we get U C star C U star, and A star is equal to U C U star U C star U star, and so that's the same as U C C star U star. Okay, now since you have that this is equal to this and U is invertible, you can get rid of U on the left, you can get rid of U on the right, and we conclude that C star C is equal to C C star. With C upper triangular. Okay, so we'll be done if we show the following claim. An upper triangular matrix is normal if and only if it is diagonal. Sorry, let me restate that. One part is trivial, so let me just state the non-trivial part. A normal upper triangular matrix is diagonal. Okay, so why is that? Right, so first, let me emphasize that if we prove this, then we're done, right? Because then the surety composition is actually a unitary diagonalization of A, right? Because we'll have a unitary matrix and then in the center, a diagonal matrix. Okay, so that's all we need to show. Now let's show this. So if you do C star C E1, then this is equal to CE1, CE1, and that's equal to the norm of CE1 squared. And if you do CC star E1, E1, then you get C star E1, C star E1. So you get the norm of C star E1 squared, right? Now, if your matrix is normal, then C star C is the same as CC star. And so we conclude that CE1 has the same length as C star E1, right? So another way of saying that is the first column of C has the same length as well as the first column of C star, but C star, remember, you obtain by replacing, starting with C, replacing rows with columns and columns with rows, and taking complex conjugates, but that's not going to modify the length. So we can say the first column of C has the same length as the first row of C. But the first column of C has only one entry, one non-zero entry. Right, C11, which it shares with the first row of C, right? So if you have these two vectors, they have the same length and the same first entry, and one of the vectors has all of the other entries equal to 0, then the other vector also has to have all of the other entries equal to 0. Hence, the first row of C is equal well, it is equal to the first column of C. Notice that it's enough for it to share it with complex conjugate, but it shares it on the nose because I know that the eigenvalues of A, which are the diagonal entries of C, are real numbers. Oh no, actually in this case I don't know that. Okay, so it shares it with the first row of C star up to a complex conjugate, right? Which doesn't affect the length. Okay, so we still conclude that the first row of C is equal to the first column of C, arguing in this way for subsequent columns shows that C is diagonal. Right. And that finishes the proof of the spectral theorem for normal operators, normal matrices. Okay, wonderful. So that's the end of the lecture. Feel free to stop listening there. I will give you now some context. In this case, I want to tell you a little about eigenvalues and geometry, which is one of the topics that I like to spend a lot of time thinking about. So let's look at an infinite dimensional setting. Okay, so consider the operator two derivatives in x, right? Just take two derivatives in the x variable, acting on the vector space of smooth functions on the interval from 0 to L. Here, L is some positive constant. Okay, so there's not much geometry here, right? We're just looking at an interval. So all of the geometry is the length, right? The only invariant is the length. And I want to know, how does this operator, or more precisely, how do its eigenvalues notice the length of the interval? Okay, so first, on this vector space is too big. On this vector space, if lambda is any complex number at all, any complex number whatsoever, we can find non-zero solutions to dx squared phi equal to lambda phi with phi in this space. Phi is smooth function, right? Indeed, if we write, let's say I write lambda as alpha plus I beta squared. So every complex number can be written as the square of some other complex number. Let's say that I write lambda as a plus alpha plus I beta squared. Then they are, so the solutions to this equation are a e to the alpha plus I beta x plus b e to the minus alpha plus I beta x, where a and b are arbitrary constants, right? You can use Euler's identity for the complex exponential to write this in terms of real, well, to find the real and imaginary parts. So you could write this as a times e to the alpha x multiplying cosine beta x plus I sine beta x, and then you would have plus b e to the minus alpha x multiplying cosine beta x minus I sine beta x. Okay, but in particular, this space is too big. There's all lambdas, all complex numbers are eigenvalues, and there's no geometry. I don't see the length of the interval anywhere. Okay, but the problem is that we're looking at too many functions. What we want to do is restrict the class of functions by imposing some boundary conditions. So it's more interesting to impose boundary conditions. So let's define D to be all of those smooth functions on the interval 0L such that phi of 0 is 0 and phi of L is also 0. So these are functions that vanish at the endpoints. We call these Dirichlet. This is known as the Dirichlet domain or Dirichlet boundary conditions. Okay, so physically, you can think of what we're doing as we have a string and we're interested in how this string vibrates. And in the first case where we're just working with arbitrary smooth functions, then the string just was too unconstrained to have anything interesting happening. Now what we're doing is we're fixing the endpoints of the string, and then we're letting it vibrate in between. So this is more physical, like if you have a guitar string or a violin string or something, the endpoints are fixed and you're strumming it to make it vibrate. So now the solutions to dx squared phi equal to lambda phi. Right, let's continue to write lambda as alpha plus I beta squared phi. But now I want phi in D. Okay, well now here's the general solution, but now I need for the function phi to be in this space, right? So I need this function to vanish at both endpoints. So that gives you two conditions. Just by plugging in the left endpoint, you have that a plus b, the constants, have to add up to 0. And if you plug in the other endpoint, you find that e to the alpha L. Here, let me just write down the. So if I plug in the other endpoint, then I'm going to get an equation from having this vanish, and I can pull out a common factor. So here I know that b is equal to minus a, so I can pull out a common factor that would be non-zero. And so then I can take whatever's left, put it equal to 0, and that's going to give me two equations, one for the real part. And then one for the imaginary part. Okay, so now let's stare. This second one, exponentials of real numbers are always non-zero, right? In fact, always positive. So this is a positive number and this is a positive number, and if I add them up, that's a positive number. So the only way this product is going to be zero, we're going to have sine of beta times L equal to 0. Okay, now if sine is equal to 0, cosine of that angle cannot also be 0. Cosine of that angle has to be either plus or minus 1. So this is either plus or minus 1, which means that this has to be 0. And if this is 0, then alpha has to be 0. So, okay, and also let's keep going with the second one. If you know that sine of beta L is equal to 0, then that tells you that beta times L is a multiple of pi. So beta is in the set, you have 0, or you have pi over L, or you have plus or minus 2 pi over L, and so on. So coming back to our initial equation, we see that there are non-zero solutions to Laplacian of phi equal to lambda phi with phi in D, in the smooth function satisfying Dirichlet boundary conditions, if and only if lambda is in the set minus pi squared k squared over L squared with k a natural number or 0. Okay, so these are the eigenvalues of this infinite dimensional operator acting on this vector space. The eigenvalues, we notice, form a sequence, right? The discrete set, a sequence that goes to minus infinity as k goes to infinity. And if you know the eigenvalues, then you know the only interesting piece of geometry there was here, the length of the interval. And so eigenvalues. Tells the length of the interval. So the fundamental tones of a vibrating string, that would be the physical interpretation of the eigenvalues. The fundamental tones of the vibrating string tell you the length of the string. Okay. For a rectangle, so say you have a rectangle and this side has length 1, this side has length 2, and now the Laplacian has to form dx1 squared plus dx2 squared. So here we would define D, so Dirichlet boundary conditions. We're looking at all of the phi that are smooth functions on the rectangle, such that phi of 0, y is equal to 0. That's equal to phi of L1, y, and this would be for all y's between 0 and L2, and phi of x comma 0 is equal to 0, and phi of x comma L2 is equal to 0 for every x in the interval 0, L1. Okay, and a very similar computation lets you see that Laplacian phi equal to lambda phi with phi in this vector space has a non-zero solution if and only if lambda is in this set. Let me give myself more space. Lambda is in the set minus pi squared, then we have k1 squared over L1 squared plus k2 squared over L2 squared, where k1 and k2 are allowed to vary among the non-zero natural numbers. Okay, now what's great about intervals and rectangles is that you can compute the eigenvalues explicitly. For a general shape, we can define the same vector space. We can look at the Laplacian, so this would still be just dx1 squared plus dx2 squared, and we can look at D, so this would be all of the smooth functions on omega, such that phi restricted to the boundary of omega is equal to 0. And you can prove an abstract existence result. So the theorem says that there is a sequence lambda j of negative numbers, lambda j going to minus infinity. So there's no accumulation points in the complex plane, such that Laplacian of phi is equal to lambda phi with phi in D has a solution, has a non-zero solution. If and only if lambda is inside this, is one of the elements from this sequence. Okay, so great. So in general, what you can say is this abstract existence result that the Laplacian has eigenvalues, and that these eigenvalues form a sequence that goes to minus infinity, right? But there's no hope for a general shape of computing what these numbers are. So there's a question, natural question. How are the eigenvalues of the Laplacian related to the geometry of omega? Okay, so here's a fun story. In 1910, the physicist Lorentz went to Göttingen, right? A university has come up in our stories before, and gave a lecture entitled Old and New Problems in Physics, in which he talked about something that was pretty new at the time, Planck's radiation formula, and how one might explain it mathematically. He conjectured that if you have any domain like omega, then the specific eigenvalues, well, those will depend on omega. But how quickly do they go to minus infinity? That he conjectured doesn't depend on omega. It should only depend on the area of omega, right? So, okay, David Hilbert was in the audience. David Hilbert was one of the greatest mathematicians of the 20th century, especially the beginning of the 20th century. And he commented this conjecture was beautiful, but that there was no way we would figure that out while he was alive. Also in the audience was a student of David Hilbert, a guy called Hermann Weyl, very clever guy. And within a year, he had proven that Lorentz's conjecture was true. It's now known as Weyl's law. So define the counting function, so n of capital lambda, to be the number of eigenvalues. So, eigenvalues of the Laplacian such that in absolute value, it's less than capital lambda, right? So how many eigenvalues do you have that are less than 10 or less than 100 or less than 1,000 in absolute value? Then Weyl proved that the area of omega is equal to 4 pi times the limit when capital lambda goes to infinity of n of capital lambda divided by capital lambda. So this is amazing, right? So this says the eigenvalues are growing linearly, and the rate of growth is gives you the area of your domain. So Weyl proved this was 1911. He conjectured, and it was proven by Victor Ibri in the 80s, that you could also get the perimeter from the eigenvalues. In fact, the length of the boundary is equal to the limit as you go to infinity of 4 pi times the counting function minus the area of omega times lambda divided all by square root of lambda. It was known before 1980 that you could recover the perimeter from the eigenvalues, but this way of recovering the perimeter from the eigenvalues wasn't established until 1980. Okay, wonderful. So if I give you the eigenvalues, the tones, so now instead of thinking of a vibrating string, it's typical to think of a drum. So think of your drum domain as giving you the drum head, and you're banging on the drum head. And so the different tones that you can produce are made up of combinations of fundamental tones. Fundamental tones are the eigenvalues of the Laplacian. And if I just tell you the fundamental tones, you can figure out the area and the perimeter. Now remember that for a planar domain, you have the isoparametric inequality. Isoparametric inequality says that for any planar domain, the length of the boundary, so the perimeter, squared, is bounded below by 4 pi times the area, with equality if and only if omega is a round ball of radius. Well, it would be the perimeter length of the boundary divided by 2 pi. Wonderful. So if I give you the fundamental tones, just the list of eigenvalues, then you know the area, you know the length, you can plug them into the isoparametric inequality, and you can check whether or not you have equality. So that tells you whether or not you have a round ball, right? So this domain, the shape of the drum, is entirely determined in the case of a round ball from the fundamental tones of the drum, from the eigenvalues of the Laplacian. So this led Mark Cash, 1966, to ask a very famous question: can you hear the shape of a drum? Right? So can you determine what shape you have just from knowing the eigenvalues of the Laplacian? Right? So in full generality, unfortunately, we know the answer, and the answer is no. So in 1991, a team of 3 mathematicians, Gordon, Webb, and Wolpert, found different planar domains that have the same eigenvalues as the Laplacian. So here are 2 domains for which that's true. These 2 domains are different, right? You cannot get from one to the other by doing trivial things like translation and rotation, reflection. And yet, it was shown by Gordon, Webb, and Wolpert that they have the same eigenvalues. Right? They did not compute the eigenvalues, but they proved that these have the same eigenvalues. On the other hand, we don't actually know the full answer to the question. If you decide that your drums need to have smooth boundaries, none of these corners. And we don't know the answer to the question if you decide that, well, it doesn't make sense to have a drum that's not convex. So it would be very interesting to find out what the answer is. So you can tell whether or not you have the round ball. You cannot tell if you don't put any restrictions. Something in between, there's work by a couple of mathematicians, many mathematicians, but in particular, a couple, Steve Selvage and Hamid Hesari, have shown that if you have some symmetry, so if something is close to the ellipse, for example, then you can find it using only its eigenvalues. So anyway, this is still a topic of research today. And we'll stop there and pick it up next time.